Back again, we have the semicircular object, and we're going to change the internal reflection by changing the circular shape. Now, what we're going to do, you see clearly that we are increasing the critical angle until we have reached exactly 90 degrees, around there. But you see clearly when I increase that angle, we will get a complete reflection. Okay, so again, the critical angle. The critical angle is the angle of incidence from the angle of refraction is 90 degrees. It is the smallest angle of incidence above which total internal reflection occurs, and we give it with the angle C, as we see in this picture. Okay. The total internal reflection takes place when the light ray is completely reflected. That means there is no refraction at all. This takes place at an angle above the critical angle. Okay. Why do we use a curved surface? Because then we can place that light ray at a normal, at the semicircular, and that's why it is easier to use a semicircular block. Okay. Now, some uses of the total internal reflection. Total internal reflection is used to send light signals along optical fibers. So actually the internet that you have nowadays actually goes through optical fiber, and there is a light signal going through the optical fiber, and it's reflected and goes through the whole system. Yeah, so we use it a lot for telecommunications as internet, telephone, and television. Okay. Total internal reflection in prisms, and I can see later the application again and see how that works with the prism. If the light is coming in a prism, we get complete total internal reflection. So at the right, the light comes in, is reflected, and then reflected back. This is also how DSLRs work. They use a prism. Okay. And here is an example of an optical fiber. The advantage of using optical fiber is that it's highly efficient. You don't need a lot of power to get a signal through the cable. Okay, and this is how a glass fiber works. The critical angle. Let's look for the critical angle for a glass air interface. The critical angle is given 42 degrees, and at a critical angle the refraction is 90 degrees. Now, we use the following equation. Now, we knew already from the refraction that the refractive index is sinus refraction angle divided by sinus incident angle. Now, sinus refracted is 90 degrees, so sinus 90 degrees is 1, and the incident is sine c, so we can easily use and rephrase the formula. Sine c is 1 over n. Okay, you need to memorize this formula and know how to use it. So sine critical angle equals to 1 over the refractive index. Now, what do we have for the water air surface? 1.33. So we plug in 1 over 1.33 makes 0.75. Then sine inverse sine 0.75 is 48.8 degrees. So the critical angle is 48.8 degrees. Okay. Not too difficult. Alright, we move on. Another question. For glass, the refractive index is given 1.5, so we can easily calculate the critical angle using the same formula, which is 44. For water, the refractive index is 1.33, and you will get a critical angle of 48.4. Okay? And you'll see the higher the refractive index, the lower the critical angle. Another example, n is 1.4. What is the critical angle? Try to calculate. Pause the video. We plug it in. 1 over 1.4. And then we get a critical angle of 45.6. Okay. Copy this one and try to find what is the critical angle of diamond. For this one, try to find the correct answer. Alright.